Right, so hello all, we're back again. As promised, this is a video just solving problem 43 from the textbook from set 7. I have already filmed this video 3 or 4 times, had some technical difficulties this morning, so I'm actually not going to be writing. I'm just going to be narrating this problem that I've solved many times now. So the video will probably be quicker. So let's look at the problem 43. A home run is hit in such a way that the baseball just clears a wall of 21 meters high, located 130 meters from the home plate. The ball is hit at an angle of 35 degrees to the horizontal and air resistance is negligible. The initial speed of the ball we're looking for, the time it takes for the ball to reach the wall, and the velocity components of the speed of the ball when it reaches the wall, assuming the ball is hit at a height of 1 meter above the ground. I actually, in the solutions I posted online, I did not take into account the 1 meter, but I think it still came out okay because the significant digits are 2, so they're rounded pretty far up, but I will correct that and repost it online. Okay, so let's take a look at what I've already done a number of times this morning. I've drawn a little diagram of what we have. We've got our little guy here, 1 meter tall. He's hitting the ball at 35 degrees from the horizontal, and the ball needs to clear a wall that is right here. It's 130 meters in the X direction and 21 meters in the Y direction. We're going to remember that the baseball player is 1 meter tall, and we're going to subtract that from our delta Y. All right, so when we first look at this problem, it appears as though we don't have enough to solve the problem. But we can use some, I don't know if they're tricks, but we can use some equations to figure out what our knowns are in both X and Y, and substitute and figure out if we can solve this. It's in the textbook, so obviously we can solve this. So delta X we know is 130 meters. We know that theta is 35, and we know that delta Y is not 11. This is 1 is 20 meters. All right, so what else do we know? We know SOHCAHTOA. So we can go ahead and write those equations out right away. Again, SOHCAHTOA sine equals cosine equals tan equals SOHCAHTOA. Okay. So we've got our little triangle here where this is the initial velocity. This would be the X initial velocity. This would be the Y initial velocity. We can use SOHCAHTOA and we can solve a few equations. So here we've done that. We have 2 variables in this equation. We have Vxi and we have Vi. And then we have our Y equations with 2 variables, Vi and Vi. Looking at these 2 equations, we can see that Vi is going to be the same in both X and Y, and time will also be the same in X and Y. So using the fact that acceleration is 0 in the X direction, we can quickly get rid of some of the variables in some of our kinematics equations. Again, those equations are posted online for you. X is usually a good place to start if we're talking about free fall because we can get rid of acceleration. So if we look at this equation right here, we know that we can get rid of that because acceleration is 0. And what we have is delta X equals Vxi t. So we know delta X, but we don't know Vxi and we don't know t. This is one equation with 2 variables. At this point, not solvable. But we can play a little game here where we take the t out, or I guess not take the t out, but solve for the t. And that will give us an equation that is only in Vi, and Vi and t are the same in X and Y. We can also solve the same equation for Vi, and we're we can then substitute that equation into one of our y equations. Now, our first question is to solve for the initial speed of the ball. So we want to see VI in our equations. So it makes more sense to solve for t and insert t into our y equations to solve for VI. All right, so let's do that. So same equation. However, this time we can't get rid of a, but a is a variable that we know. We can get rid of the t's by inserting this equation in. We can also get rid of the VYI by substituting this equation in. So you can see I've done here. And then what we'll have is an equation in only VI. That'll be the only variable that we don't know, and we can solve for VI. So let's go ahead and do that now, which I've already done. We are inserting t here. We are inserting t here. Make sure that you remember to square it. It's really easy to forget to square that t. 20. So we see that the v's cancel out. Sine, we're left with sine 35 over cosine 35 times 130. And we know that sine theta is opposite over hypotenuse. We know that cosine theta is adjacent over hypotenuse. If we have cosine 35 over sine 35, what we have is opposite over adjacent because the h's cross off, and that's tan. So we can just stick a tan 35 in for the sine over cosine, which we've done here. And then this is just a bunch of numbers except for the VI squared, and we want to solve for the VI squared. So if we plug these numbers into our calculator, what we get is this right here. We want to solve for VI, so we're going to shove VI over here. We're going to shove the 20 over here, and what we end up with is this. Take the square root of VI squared, you get VI, take the square root of that number, and what you end up with is something that looks like 41.69 or 42. So our answer for VI is 42. So this is 42 meters per second. All right, so B is asking us for the time it takes for the ball to reach the wall. We could have, instead of solving our problem for t, or instead of solving our problem for VI, the last one we could have solved for t. But since we wanted VI first, we got VI first. Now we can take the VI that we've gotten and we can just plug that into simple equations and solve for t. So let's go ahead and do that. As you can see, I've done that here. We found above that t equals delta x VI cosine 35. That's just a bunch of numbers. We're going to plug in the numbers and we get 3.778. Using the two significant digits, we get 3.8 seconds. That is our solution for time. All right, so C. C says the velocity components of the speed of the ball when it reaches the wall the actual paper book also asks you to find the magnitude of the speed of the ball. So I've done that as well. I guess if you're looking at this book, you don't need to do that. Not sure why they don't ask you to do that, because I think that's a good idea. Oh, no, it does. The velocity components and the speed of the ball. Okay, I read that incorrectly. So it is the same as the book. Okay, sorry, moving along. So we're going to start with, again, simple equation because A is 0 in the x direction. We're going to go delta x equals VFX t because we're solving for VFX and VFY, so we can solve for the speed. So if we plug in what we know, which I've done right here, we get VFX equals 34 meters per second. Vy is not as simple because, again, we have acceleration. So if we use this equation from our kinematics equations, we plug in what we know again. So this is what we're solving for. We know that VIY equals VI sine 35, and we solved for VI earlier. AT, we know that A is negative 9.80 meters per second, and we know that T is 3.8 seconds because we solved for that already. So then we can solve for VFY, just plugging in numbers and the equations that we solved for earlier. Okay, so now we have VFX and we have VFY, and we're looking for the speed. So what is that speed? That is the magnitude of this triangle. So if we draw a triangle, this is 34 meters per second, and this, that is negative 13 meters per second. What we see is a right triangle, hypotenuse, opposite, adjacent, and we need to solve for the hypotenuse because the speed of the ball is just the magnitude of this vector. All right, so if you recall from one of our first tasks given, I think it's actually the first document that professor posted online. He posted the SOHCAHTOA equations, and then he also posted this one, which could be written like this. So we're going to solve for the hypotenuse of this triangle. And in order to do that, we're going to square 34, we're going to square negative 13 and take the square root of it. And what you end up with is 36 meters per second. Okay, so that was a mouthful. I realized that I wasn't writing while I was doing this video because I did already. I hope that this is still helpful and that I didn't rush through it. I guess you can pause it and look at it because it's a video. If this was not clear enough for you, if you're still confused about how to solve these problems, please reach out to me. I am not available all the time, obviously, but I can make a meeting for you. If you want me to write on the board back there, I can do that in person. If you want to meet in Teams, I am here to help you. Please reach out if my videos are not clear or if you need additional help. You've got my email. I will be posting this soon, and then I will see you next week. Thank you.